Hi, everybody. Welcome to week 3. Today, we're going to focus our lesson on light, and we're going to be headed into chapter 4.
So we're going to start by taking a look at this picture. What do you notice? Can you see both images in this one photo or this one drawing? Do you see the young lady and the old lady? I want you to keep this picture in mind as we look at how light can act in 2 different ways. This picture has 2 images in it. Light has 2 ways it can behave.
And those two ways are going to be they're going to be in the form of energy and in particles. Prior to 1900, scientists felt that light only traveled in waves. Okay, but after 1900, scientists did some experiments and they found out that light also acted like particles. So it was a very big mystery for scientists.
So first, light as a wave. We use an electromagnetic radiation to describe this, and that describes the light energy that comes in waves, and it says that each different amount of energy that wave of light can have will give it specific characteristics. So before we get into that, and the next slide has another definition of that on there, but before we get into that, we have to look at the parts of the wave. You'll notice there's also a reading attached in your resources for this week that talks about the properties of waves too, the different characteristics. So they're all going to have these main ideas. So you have amplitude, wavelength, frequency, and then crest and trough. The amplitude is how high the wave is. So from the origin to the peak. So in this case, that x-axis all the way to the top of the wave. That's the amplitude. The wavelength is how the distance between 2 waves. So we have this point on the wave and it continues, and at this point of the wave, it's going to start repeating again. So that unit that keeps repeating over and over again is how we measure the wavelength. And we describe it by the distance between 2 successive or in a row wave crests. This is measured in nanometers. The frequency of the wave is how many times it goes up and down in 1 second. So how many times it completes a cycle in a second. So you have a high frequency, which goes many times in a single second, compared to a low frequency, which doesn't go as many times in a single second. And then last, we have crest and trough. The crest is the highest point, and the trough is the lowest point.
Okay, so we deal with light, we come to a very, very, very important number called the speed of light, okay? The speed of light is a constant, so you have to remember that when we're dealing any form of light, we are going using that it is traveling at the speed of light, which is 3.0 times 10 to the 8th meters per second. Put it into regular numbers, that's 108,000 miles per second. So what scientists found out is that the speed of light, which c, is equal to frequency times wavelength. We put in there Greek letters to show what the formula looks like. But what we really want you to take away with from this slide is that this is a constant, and then the relationship between frequency and wavelength is going to be determining, or it's going to be, when you multiply together, will give you that constant. So the big takeaway is that question that's on the bottom. How are frequency and wavelength related? Is it a direct or inverse relationship?
And if you said inverse relationship, you'd be right, which is what's on this next slide. So the electromagnetic spectrum is the collection of all the known frequencies and the wavelengths that match them. And you can see that these long wavelengths don't come out as often. They can't cycle through as quickly. So a long or a big wavelength has a low frequency. They're opposites. This is an inverse relationship. Versus these very short wavelengths down on the other end are really frequent. They're moving up and down a lot. So they have a high frequency when there's a low or short wavelength. So this is just that diagram in the middle really shows us that relationship. So how does that relate to this electromagnetic spectrum? Well, that's describing how these different waves behave. Radio waves, microwaves, infrared, all the way to gamma rays. In the middle of that, you have the visible spectrum. The visible spectrum are the waves of light that we actually see. We can't see UV rays. Can't see the UV rays that are giving you a tan or unfortunately a sunburn, but they're there. They have a higher frequency than the light we see. So if you imagine that rainbow, when you see a rainbow, that RGB, red, orange, yellow, green, blue, indigo, and violet, the red is always at the top or on the outside of that rainbow, has a long wavelength. Infrared, or kind of we refer to this as heat waves, right? That's the waves, the energy that's given off in heat. That's a longer wavelength than what we see in visible light. And like we said before, UV is the shorter wavelength. So this is just kind of giving you an idea. There's numbers attached here, and you're going to see this diagram again. But it just shows that relationship, that they are opposite. And that's our big takeaway here. Long wavelengths have a low frequency. Short wavelengths have a high frequency.
So the third variable that enters to this equation is energy. Okay, so if we know the wavelength, we can calculate what its frequency is. If we know what the frequency of a wave is, using a constant known as Planck, we can actually determine the energy of a particular wave. Okay, so the first equation has to deal with an inverse relationship between wavelength and frequency, whereas this takeaway is that there's also a relationship between energy and frequency. And because the constant is on the right of the equation this time, you're going to notice that it is going to be a direct relationship. So if frequency goes up, energy is going to go up.
So how does this relate to the model of the atom? Well, remember back to the Bohr model of the atom. You have the nucleus in the middle and you've got the energy levels drawn. So this is on the diagram on your screen now is Bohr's hydrogen atom. And he had the electron in its ground state, which is at the normal place. It's going to be where it's most stable and it's closest to the nucleus. What happens is light shines on these atoms and gives these electrons more energy. And when those electrons have more energy, they get excited. They have more energy, they have a higher frequency, and they jump to another energy level. They're not happy here, they're not stable here, and they don't want to stay here. So as soon as possible, they're going to release that energy and drop back down to their ground state. That's when radiation is emitted or given off from that reaction.
Okay, so this slide is going to show you in picture form what Mr. Riley just was talking about. So I'm going to start here on the left. So this is an atom, and we are following Bohr model. We have energy levels as we get further away from the nucleus. This little dot here is an electron, okay? What you can see here is that this is energy that's coming in the atom and the electron is gaining it. So right here, the electron ground state, and then when it gains energy, it jumps to the excited state. As Mr. Riley said, it doesn't like to be in the excited state, so what's gonna eventually happen is it actually will emit energy in the form of a color wave or type of radiation wave, and it's going to return back to its ground state. What you can see here, the difference is, can you see the picture that this is a high frequency wave, which means it's going to be energy. So this electron is able to jump 2 levels. This is a longer wave, so it is a shorter frequency, a lower frequency, which is lower energy, which is only allows 1 energy level. So those relationships that we talked about are very important. And what this whole slide is dealing with is something called a quantum. You will never, ever, ever find an electron in between energy levels. What Planck says is that the electrons gain energy form of a quantum, which means that they will be here, or they'll be on this line of the energy level, or they'll be on this line of the energy level, but they will never be where the moon is now. They'll never be here or be here. They will only be on the energy level.
So that brings us to something to think about. Why are these signs all different colors? why does this one burn a red and this is green and this is multicolored, which isn't a sign, but why is the light burning in different colors? Well, think about hydrogen. You might remember these gas discharge tubes from freshman year in integrated science. And when you looked at the gas discharge tube through a spectroscope, you saw the different bands of light that were produced from hydrogen gas being burned or electricity passing through it. So what happens is, as the light passes through the spectroscope, it's bent with a prism. And now you're going to just see the individual bands of light that exist in the hydrogen atom. This is very simple because there's only one electron in a hydrogen atom. So you're only going to see 4 distinct bands of light. Notice that the violet colored one has the shortest wavelength and the red colored light has the longest wavelength. This relates to how far the electron has jumped, just like Mr. Harfinist was saying. That long wavelength for red light didn't have a lot of energy, it had a low frequency and low energy. So it was only emitted when that electron jumped 1 energy level or fell back to one energy level, compared to the violet colored one at 410 nanometers. Short wavelength, high frequency, high energy. It jumped, or it fell back 4 energy levels when it released that light. So the farther the jump or the fall, the more energy that was transferred, whether it's absorbed or released.
Okay, so we've already talked about it acts as a wave, but it can also act as a particle. Man, you probably know Albert Einstein used Planck's equation and proposed that light existed in quanta of energy that acted like particles. And all these particles, photons. And what Einstein said was that each photon carries an amount of energy that can be calculated by Planck's equation. So really what he is saying is that the relationship between light acting as a wave and light acting as a particle. So you can still calculate the amount of energy, you can still calculate the frequency, you can calculate the wavelength. What he found out is that when the photon strikes the surface of an object, it either has enough energy to eject an electron or it doesn't. So he probably found out that red light might not have enough energy to eject an electron, but blue light, in the case of this picture, does. And you see this is just a depiction of it, and of the photoelectric effect, and you see this during photosynthesis, which is something that you all talked about last year.
So the bottom line is that light can act as a wave or as a particle. But teaser for next week, can matter act as a particle and a wave?
Oh, I guess we have to wait for 2 weeks because you're off next week. So have a wonderful vacation, and we'll see you or talk to you in the later part of April.
All right, enjoy your vacation.
Bye.